Okay, we're now live. So welcome everybody to the Sun, Our Star session this afternoon. So I'd now like to start by introducing Dr. Helen Mason. Helen is a solar scientist at the University of Cambridge and has worked on many joint UK, NASA, ESA and Japanese space projects. So we're incredibly fortunate to have her here with us today. So thank you, Helen. She works closely with teachers and students throughout the UK, most recently leading the project sunspaceart.org. And you can find out more about that project in the Sun Space Art exhibitor booth. So I'll now pass you over to Helen. Thank you.
Thank you very much. I'll just share my screen. Right, I'm going to bring a bit of sunshine today, I hope. It's a little bit cold and windy out there, so let's get a bit of sunshine. I'm passionate about the sun, as Becky said, and I work at the University of Cambridge. I'm a solar scientist. I've worked on many solar missions for decades. I'm also an STFC Leadership Fellow, which means I do a lot of outreach work, in particular with schools. This picture that you can see here is a picture of the sun taken from space. So I work mainly with space observatories. And on the right-hand side there, you can see a huge eruption on the side of the sun. So this picture is taken with the Solar Dynamics Observatory, and I'll come back to that in a minute. We have been living through an amazing golden age of solar space observations. In the past 2 decades, we've had SoHO, which is an amazing solar observatory, which I'll tell you a little bit more about later on. I've worked on that with colleagues in NASA and ESA over at the Goddard Space Flight Center. We've had other UV observatories, X-ray observatories, and more recently, we've had Parker Solar Probe and Solar Orbiter. Obviously, I can't tell you all about those in the time I have available, but I will just give you a little idea of what we've been doing and what we've observed and what we've learned from these observatories. So just start at the beginning with a few facts about the sun. The sun is just a middle-aged star. It's about halfway through its lifetime. It's about 4.5 billion years old, and it's going to carry on for about another 6 billion years. That's a very long time. We don't really need to worry about it. It will eventually grow into a red giant. The outer atmosphere will explode off, and the inner core will turn into a white dwarf. It's our energy source. It gives us almost all the energy we need here on Earth. It's huge. And if you can see the little sunspot there in the middle of that picture, that's about the size of the Earth compared to the sun. So you can fit over 100 Earths across the sun and 1 million Earths inside the sun. It's a long way away, and it takes light, about just over 8 minutes to reach us from the sun. It's massive. It takes up almost all the mass in the solar system. And the surface of the sun is around about 6,000 degrees, just below 6,000 degrees. So how's that energy produced? Well, the energy is produced in the core of the sun with hydrogen turning into helium through Einstein's equation. A little bit of mass turns into a huge amount of energy. The core of the sun is at 15 million degrees. That energy then propagates out through the different layers, takes quite a long time. Then just beneath the surface, it's transferred by convection. Here we can see the sun in the visible. We can see a lot of sunspots. Now, these sunspots are quite important because they're characteristic of how active the sun is. The sunspots represent regions where the magnetic field on the sun is very strong. And sometimes there's a lot of sunspots, and sometimes there's very few sunspots. And this is about an 11-year cycle. When there's a lot of sunspots, we get beautiful phenomena like the northern lights, aurora. The image down the bottom, the sun is spinning. Well, the sun does spin. It takes about 25 days to spin around on its axis at the equator, a little bit slower at the poles. Now, if we go back in time, one of the first people to observe the sun was Galileo. Of course, Galileo was one of the first people to use a telescope to observe the planets and the moon. He was also very interested in the sun. And this is where I say to you, do not ever look at the sun. The sun is far too bright. You must not look at the sun. Project an image of the sun, or you can use a very special solar telescope to look at the sun. He projected an image of the sun, and he saw these sunspots, and he saw the sun spinning. As you can see, these are his actual drawings And he was able to see that the sun was taking 25 days to spin around, and he associated these sunspots with the sun. Now, Galileo was always getting into trouble. He got into trouble for his observations of the planets, for confirming what Copernicus had said, that the sun is at the center of the solar system, not the Earth. They thought in those days the Earth was so important, it must be the center of everything. But he also got into trouble by saying that these sunspots were actually on the surface of the sun, because the sun should have been a perfect astronomical body, like the stars. It is our star, it's our nearest star, and we can observe it in a great deal of detail. And if we can understand our star, then that helps us understand the other stars and the other objects. This image here, this graph, shows you the sunspot number along the y-axis and the year. And it shows you how the number of sunspots goes up and down with an 11-year cycle. And this is caused by the magnetic field on the sun, which has an effect of erupting through the surface every 11 years and then decaying away again. Now, this is an awesome phenomenon, which some of you may have experienced. If you haven't experienced, then please take the opportunity to do so. There's an eclipse coming up, which in the United States in 2024. But it's one of the most awesome natural phenomena that you can experience. Now, the moon is just the right angular size. Of course, it's not the same size of the sun. It's much smaller. It's much smaller even than the Earth, but it's much closer to the Earth. So it's just the right angular size to block out the disk of the sun. And the disk of the sun is about 1 million times brighter than this crown of light that we see, which is called the corona, which is actually the atmosphere of the sun. So normally we can't see it because the disk is too bright. But when the disk is blocked out by the moon, then we see this corona, this crown of light. And you'll notice that it has a lot of structure there. And that structure is caused by the magnetic field on the sun. So it's actually tracing out the magnetic field on the sun. And it's doing that because that hot gas in the atmosphere is actually charged. Now, I'm passionate about the sun. I'm passionate about solar eclipses. And I've been very fortunate to have actually experienced 3 of them. And it's not just what you see, which is beautiful. And that's the only time during a total eclipse that you can actually look at the sun without special eclipse glasses, when it's in totality. But it's also all around. It goes very quiet, it goes very cool, it goes very dark. And it's as if the sun has suddenly gone out, and it's actually quite frightening. The last eclipse I saw was in 2017, and it was one that went right across the USA. And I was very fortunate to be at the Smoky Mountains National Park, the NASA's representative in solar physics, and was able to participate in the celebrations there. We were up quite high in the mountains, and it was just awesome. We could see like a pink sunset all around us. Now, sometimes people in days gone by didn't understand what was happening. So they had to make up stories. And there's a story of the ancient Chinese made up about the dragon eating the sun during an eclipse. But the Cherokee Indians lived in the Smoky Mountains, and they believed that a giant frog was eating the sun during an eclipse. So we had to watch out for giant frogs when we were over there. It was a wonderful experience. Also during eclipse, sometimes you can see little red patches around the sun. And this light comes from a layer between the surface of the sun and the corona called the chromosphere. And this light is red light it's giving out there, in the red part of the spectrum, and is rather beautiful. So the chromosphere has a very complicated structure that we also need to understand. It's a little bit like twisted grass blades. It's coming up from the surface of the sun. If we look at the surface of the sun itself, we can actually observe this from ground-based observatories. And the most recent observatory that we have is called DKIS, the Daniel Hinode Solar Telescope, which is actually in Hawaii. There you can see it. It's actually operated from the USA, from Boulder, but it's there in Hawaii, beautiful location. And that movie that you can see there, if I just play it again, is actually the surface of the sun bubbling away. So that's those big convective cells underneath the surface, bringing up the hot gas. We call it a plasma, but when it's ionized hot plasma, bringing it up, like something boiling, a porridge boiling on a cooker or something like that. Going back a little bit in time, Newton was very interested in the colors of light. Of course, Newton is famous for many different things. He's famous for gravity, for asking the very simple question, why did the apple fall down? And for learning about the laws of gravity that keep the planets orbiting around the Earth. He also was very interested in astronomy, and he built his own telescope. And that telescope was what we call a reflecting telescope with mirrors rather than with lenses. Galileo's telescope had lenses. But he was interested in the colors that he saw through his telescope and why they were there and what they were. So he did some experiments with a prism to break up the colors of the rainbow, colors that you see during a rainbow. And he was able to determine that what we call white light is made up of those colors of the rainbow, if we can split it up in different ways. We use a very specialized instrument called a spectrometer to find out even more information about the colors of light. If we split it up using this instrument called a spectrometer, which has a slit, sometimes we're able to see some bright lines at different positions coming from the gas that we're looking at, or sometimes if we pass the spectrum, the rainbow colors through the gas, we get these dark absorption lines. And this tells us about the makeup of the hot gas, what it's made up, the elements it's made up, but also lots of different information about it, its temperature, its density, etc., etc. I won't go into too much detail about that, but that is my area of speciality, being able to understand the spectrum of the sun. And here is an example where you can see the different elements, hydrogen, helium, nitrogen, neon, argon, and mercury, and they all have these characteristic, we call them spectral lines, these bright emissions at particular wavelengths, at particular places. And it's a little bit like the bar charts that you get in a supermarket. When you scan it, you know what products being bought, etc., and everything about it. Well, this spectrometer gives us information about the light that's coming from the sun, and indeed the light that comes from other stars. Helium itself was first discovered on the sun, and there you can see a picture taken in just that helium line. But we don't have to stick in the visible spectrum. We can go beyond the visible spectrum. We can go into the infrared, microwaves, radio, or in the other direction, we can go beyond the violet into the ultraviolet, X-rays and gamma rays. And indeed, if we want to observe the sun in the ultraviolet or in the X-rays, we do need to go into space because we need to get above the Earth's atmosphere in order to be able to observe in certain wavelengths. So a lot of the space observations I'll be telling you about will be in the ultraviolet and taken with a space observatory. Now, I told you about the corona, which is the atmosphere of the sun. And when people observed that in the visible during an eclipse and used a spectrometer, they couldn't understand these lines, these spectral lines that came from it. And it took them a long time to realize that actually, even though the surface of the sun is only about 6,000, this corona, this atmosphere of the sun is very, very hot. This atmosphere is 1,000,000 degrees. This was totally unexpected. They didn't expect to find that. They expected that as they moved away from the sun, it would get cooler, not that it would get hotter. So it's 1,000,000 degrees. And one of the things as scientists we've been trying to understand, and we've made some progress, is why that solar corona that we see during an eclipse is so hot. Why is it 1,000,000 degrees when the surface of the sun is only 6,000 degrees? Now, because it's 1,000,000 degrees, it emits very strongly in X-rays and ultraviolet. And this is a picture taken with a satellite which can see the X-rays. Of course, our eyes can't see X-rays, so this is taken with a special camera which is sensitive to X-rays, and we colored it orange. It's a Japanese satellite called Yoko. And you can see it's a very strange features. It looks very different from the visible pictures that I showed you earlier on. It's got some dark regions. And these are regions where the magnetic field on the sun is open. Because that corona is so hot, it means it's charged. It's got a particular charge and it follows the magnetic fields. And in those, we call those dark regions coronal holes, or holes in the corona. The material flows out into space into what we call the solar wind. The very bright regions you can see there are where the sunspots are. And that's where the magnetic field is closed and that gas, that plasma, that hot plasma is trapped. So we have different regions on the sun depending on what the magnetic field on the sun looks like. And this is in X-rays because the hot gas emits very strongly in X-rays. So SoHO is one of the best solar observatories we've ever had. It's over 20 years old now. It's still operating. I worked on SoHO from before launch. You have to prepare the instruments, you have to work, you have to coordinate the observations, but it is still operating. Now, in some cases, we've got better instruments now, so we've switched some of the instruments off, but some of them are still being used and it is still operating. So it was launched in 1995 in December, and it had different instruments on board to study different aspects of the sun. It was able to study the solar interior by looking at small motions on the surface of the sun. We call that helioseismology, just like you have seismology here on Earth, which looks at the interior of the Earth. It had instruments which were used to study the solar atmosphere, the corona, and those were the ones that I was mostly involved with and working on. It had instruments to study and to sample the solar wind, so the material that flows out of the sun. And SoHO is in a very strange orbit. It's not orbiting around the Earth like most satellites do. It's actually orbiting around the sun with the Earth. So it's 100th of the way between the Earth and the sun, is orbiting around the sun, and that means it sees it 24 hours a day. This is an image taken in the ultraviolet from SoHO. And again, you can see those dark regions, those coronal holes where the magnetic field is open. So what you're looking at here is gas, is plasma at 1,000,000 degrees. You're looking at the solar corona. Of course, we can't see ultraviolet, so we've had to color it. It's taken with a camera that can see ultraviolet, and we've colored it green. We could have colored it pink or purple or any color we like. But in this particular time, for this particular set of observations, which is showing us the gas at 1,000,000 degrees, we've colored it green. And you can see how beautiful it is. And you can see the dark regions, coronal holes, but you can also see those very bright regions. We call those bright regions active regions, and that's where the sunspots are. Now, more recently, we have another observatory that I mentioned first, right at the very beginning, called the Solar Dynamics Observatory. And this was launched in 2010, so it's not that young anymore, but it's still working and still giving us amazing observations of the sun. Again, we're looking in the ultraviolet at the sun, but we're looking in much, much more detail than we could with SoHO. So we look at the detail. We can see at about 1,000 kilometers. We can see a lot of detailed things happening on the sun. And we can look at different wavelength bands, which show us different temperatures. So here, going from the left-hand side at the top, that band is sensitive to 5,000 degrees. Going through to the bottom, it's about 1,000,000. And then going up again on the right-hand side, that goes up to very high temperatures, up to 10 10 million degrees, and we can see explosions on the sun. Now we can see the whole sun, the full disk of the sun. Every 12 seconds, we get an image, and you can see these images for yourself. If you Google Solar Dynamics Observatory, the sun today, you'll be able to see what the sun looks like today from space, from the Solar Dynamics Observatory. Now, this gives us a lot of information because we can see how structures change at different temperatures, and we can build models to see whether what we think should happen is actually happening at different temperatures. So what we can see are these huge loops of hot gas in the ultraviolet. As you can see on the right-hand side, that's a picture in the ultraviolet on the edge of the sun. And it's as if we've got the magnet, we're tracing out those magnetic fields. It's as if we've got a magnet lying there. And those foot point regions where the loops are rooted, that's where the sunspots are. That's where the magnetic field is very strong, and that's where the sunspots are. Sometimes we have huge explosions on the sun. When we get a lot of sunspots, when we get a lot of active regions associated with the sunspots, sometimes the magnetic field gets very twisted up. The magnetic field doesn't like to be twisted up. If it gets twisted up, it tries to break and go into a smoother loop-like structure, as we saw. And when it breaks, the magnetic energy is released into heat and into motion. So we get materials shooting out into space, or we get solar flares. And solar flares are regions where very fast release of energy, we can reach very high temperatures above 10 million degrees. And that means we get very bright emission. It's very strong in ultraviolets, in X-rays. In fact, the strength of a solar flare or a solar explosion is measured by the amount of X-ray light that comes from it. And it starts off A, B, C, M, but up to X. X is a very large solar flare. And here we can see a solar flare taking place in the ultraviolet on the edge of the sun. And then we see these huge loops of very hot gas developing. And we want to study the development of solar flares and why they happen and how they erupt. Now, sometimes this is like a corona. This is called a coronagraph. So it's simulating a corona in that we've blocked out the disk of the sun. If you see that white circle there, that's where the sun is. And sometimes we see, and that we can see huge amounts of material shooting out into space. And here we call these a coronal mass ejection. And here you can see billions of tons of material moving at very high speeds. So we sometimes see these more frequently during the active times than we do during the quiet times. And here's a similar coronagraph. And there you saw a couple of comets to begin with. I'll show you that movie one more time. Watch out for a couple of comets going around the sun. And then you can see material shooting out into space. And here's another one. We've put the sun back there so you can see where the sun was, but the sun is actually blocked out. I'll run it one more time. You can see something lifting off from the sun and then shooting out into space. Now, we're very interested in why coronal mass ejections happen, what causes them, how they develop. But actually, we're also interested if they're coming towards the Earth. Some of them are going away from the Earth. We're interested in them, but it doesn't really affect us. Now, this is not to scale, of course. There's the sun on the left-hand side, and there's the Earth. Sometimes these explosions, coronal mass ejection, can shoot towards the Earth. Now, what you can see depicted there is the magnetic field of the Earth. So the Earth is protected by its own magnetic blanket. The material that comes out from the sun is magnetized. It can hit the Earth's environment, and sometimes it doesn't cause it any problem at all. It just scoots around the outside. But sometimes it can hit it very suddenly, and it can cause the magnetic field in the Earth's environment to change. And when it changes, that can shoot particles back down into the upper atmosphere of the Earth, giving rise to the beautiful aurora that I mentioned early on, the Northern Lights. And here's a picture of the Northern Lights taken from the International Space Station. I've never seen the Northern Lights. It's one of the things I really, really want to see. Sometimes they've been quite far down in the UK. I don't know whether they've been as far down as Swindon, but If we had a really big solar flare, they might go that far down. But besides causing beautiful effects like the northern lights, these coronal mass ejections, solar flares, what happens on the sun, can be problematic as well, because they can affect satellites. In fact, they can damage them and knock them out, make them so they're not usable anymore, can cause electricity blackouts, can affect aircraft flying over the polar regions, and can be very hazardous for astronauts who might be doing a spacewalk, or who might be on a mission to the moon or somewhere else. So we need to understand what happens on the sun and how it affects us here on Earth. And that area of research is called space weather. And at the moment, that's an area which is developing very quickly, so that we have our own capacity in the UK to understand it. And a lot of that work is now being done at the Met Office. They predict ordinary weather, but they also now have a section working on space weather. So gas flows off from the sun, hot ionized gas. It can come off as these coronal mass ejections. You can see on the left-hand side, it can flow from those open regions, and it can flow from other regions around the active regions. And we need to be able to understand that connection between the sun and the solar wind and the Earth. Now, this little picture here shows you what's happening with what we call the solar cycle, the number of sunspots. I said it goes up and down. I've just got an X-ray image in the background there, but there's year along the bottom, and there's going up and down in intensity of the sunspots and the solar activity along the y-axis. And we can see the year 2020 is just on the edge of that, on the right-hand side of that plot, and you can see that we're going down into a very quiet phase. Well, we've been through a very quiet phase. We're in 21 now, and we're just starting to see a few sunspots. So we've been through a very quiet phase in the solar cycle, without very many flares, without very many sunspots, but it's just beginning to ramp up again, and we're just beginning to see a few active regions. Now, in the last couple of years, we've had some satellites which are going very close to the sun. And in 2018, Parker Solar Probe, which is a NASA satellite, was launched. And that's called the Mission to Touch the Sun. And that's actually going very close to the sun and has already been round the sun a couple of times. It's named after a very famous solar scientist, stellar scientist, astronomer called Eugene Parker, and you can see him there watching the launch of Parker Solar Orbiter. Now, this is quite extraordinary because very rarely, in fact, it never is a satellite named after somebody who is living. So it's a very, it was a very special day for him to be able to watch the launch of a satellite named in his honor. And he was one of the first people to study the solar wind and also to study the heating of the solar corona. So as I said, the orbit goes around the sun and has been around the sun already, very close to the sun, gets quite close to the sun there. It'll keep getting closer and closer as it goes around. And it's using Venus as well. It's using the gravity of Venus to pull it closer to the sun. Now, another mission that I wanted to tell you about is Solar Orbiter, and this is a European Space Agency, an ESA and a NASA mission, and that was launched in February 2020. Now, we all know what happened around about March 2020. We all went down into lockdown. We've got the COVID pandemic. But this was launched just before. Many thousands of people went to the launch, and it was a very successful launch. But then thereafter, all of the engineers and scientists at ESA and NASA had to work remotely to test out all the instruments and to make sure they're all working, to switch on the satellite and to maneuver it. So some of them had to do this from home, which is quite extraordinary, working under difficult conditions. But both Parker Solar Probe and this is the orbit. Now, one thing that Solar Orbiter will do is it won't stay in what we call the ecliptic plane, which is the plane of the sun and the other planets. It'll go a little higher, so it'll be able to see the north the north pole of the sun, so to be able to see the polar regions on the sun. It won't go quite as close as Parker Solar Probe is going, but it has some other very positive features, which I'll just tell you about in a minute. Both Parker Solar Probe and Solar Orbiter have produced some initial science results, and some very interesting new things have occurred. One of these, I'm just giving you one example here, is that this is pictures taken in the ultraviolet from Solar Orbiter, and what they found was that there were small explosions happening all over the sun. They called these campfires, little explosions, which they think could possibly be connected with the heating of the solar corona. So these images that you can see there are showing you the gas at about 1 million degrees. And it can see in a much greater detail than anything's been able to see before. So if we compare Solar Orbiter with Parker Solar Probe, Parker Solar Probe stays in the ecliptic plane, but it goes very close. Now that's 0.046 of an astronomical unit. An astronomical unit is the distance between the sun and the earth. So it's going very close to the sun. It has to have special heat shields in order to be able to do this. It only has in situ instruments, that's measuring the magnetic field, the solar wind, energetic particles, and waves. It does actually have one instrument which looks at the solar wind that flows away from the sun, but it doesn't have any instruments that actually get pictures of the sun itself. Solar Orbiter goes out of the ecliptic, so it sees the polar regions, and it goes close, but it doesn't go as close as Parker Solar Probe. It'll go to about 0.3 of the distance between the sun and the earth. But it also has, besides in situ instruments, which are sampling the solar wind, it also has instruments on board which are looking, we call those remote sensing, which are looking at the sun. And one of those I'm very excited about because it's actually a spectrometer, so it will be able to study the material on the solar surface. So what Parker Solar Probe and Solar Orbiter are trying to do is to connect what's happening on the solar surface with what's happening in the solar wind that flows away from the solar surface. So I just want to finish up by telling you a little bit about some of the outreach projects I've been doing most recently. And this is a project called Sunspace and Art, and that's the website. And this brings together scientists, professional scientists, and professional artists to work together. We're working with visual artists mainly, and we've got a team of 10 of us, and we work together with schools, running workshops, which combines the science. We talk about the science of different aspects of space, for example, Tim Peake there up in the left-hand corner, and astronomy as well, the solar system. And then we get the students to do some creative activities relating to that, and reinforcing what they're learning, but also being creative in what they're doing. Down in the left-hand corner is the artwork from one of our artists, Helen Shell, and it's a beautiful sundress done in smart materials, using the different materials. So on Monday, last Monday, we had a very special festival which lasted 12 hours from 11 o'clock in the morning till 11 o'clock in the evening. And it was a STEAM. It wasn't the same STEAM as the Swindon Festival, but it was STEM and arts. So it was bringing together the science, the space, the astronomy, and arts. And that's arts, crafts, artists, music, poetry. I doubt that many of you were able to join us on that day. Many people did, but if you weren't, don't worry, because we now have the videos up on YouTube, and you can access them on YouTube. And if you look on the sunspaceart.org website, you can see the schedule for the day as well. There were lots of different talks and activities, starting with children during the daytime, running through to adults in the evening. So I've finished. I just wanted to give you some contact details. Hopefully we'll have some time for questions now, but if I don't get through all the questions, or if you want any more information, there are some contact details for you. I do tweet quite a lot on my Helen_HM11 about things to do with space, to do with the sun, and to do with educational activities. So thank you very much.
Thank you very much, Helen. That was really interesting. I learned lots, so thank you, and I'm sure everyone else did. So we've got, I think, 10 minutes for questions. So we'll see if we can get through as many as possible. So first of all, does SoHO ever need repairs, and how is that done?
That is a very interesting question. Yes, indeed. SoHO broke down about 2 years after, well, right, repairs. Okay, let me say, repairs on a solar maximum mission that I worked on previously did need repairs, and that was repaired by the space shuttle. But SoHO, it would be a bit more difficult to repair because of the position it's in, 100th of the way between the Earth and the Sun. So we wouldn't be able to go out and repair it. But what I was going to say was that SoHO was actually lost 2 years after it was launched. We lost contact with it. Now, it has an automatic mechanism to bring it back to the sun so that it can charge up the solar panels. But something went wrong, and the person who was operating it didn't realize that some of the software had been changed and hadn't been documented, and we lost it altogether. So the power ran down. And we thought, well, that's it, we've lost it. But actually, the ESA engineers and the NASA engineers got together and they looked at all the data, and they were able to try and find out what was happening to it. And in the end, they used a ground-based telescope from Arecibo to actually find it. And they were able to find it again and actually bring it back to life, by which time it had frozen. So we were a little bit worried about saying, oh, wow, SoHO's back, because we thought, well, the instruments might not work. You test instruments within a certain temperature range, and this had gone way too cold. But actually, they managed to get all the instruments back working again, and some of them were working even better than they had before. So no, we can't actually get out and repair SoHO, but and we have done with previous satellites like Solar Maximum Mission, but we did get it back operating, and then it was operating for another 20 years.
Great, thank you, Helen. Our next question is, what is the solar probe made of to resist the heat?
Now that's an interesting question. My understanding is that it's made of some carbon composite material that actually is very heat resistant. I don't know the technical details of it all, but I think that it has to reach very high temperatures, so it has to be resistant, but also you have to protect the instruments as well, so they have to kind of hide behind the shield. Now, because it's orbiting around the sun, communication with it isn't necessarily always very good when it's around the back of the sun. Radio communication is not great, so it has to all be automated. So one of the very clever things about Parker Solar Probe, for example, is that it has to always be pointed so that the instruments are protected by the heat shield, and that all has to be done in an automated way that it keeps pointing towards the sun. So I think that there are a lot of technical challenges, huge number of technical challenges with both Parker Solar Probe and with Solar Orbiter, but I'm not a specialist in engineering, but I know that those challenges are there.
Great, thank you. And next, where does the eclipse come from, and is it covered with a planet? Okay,
an eclipse is caused because the moon comes between the Earth and the sun. Now, the moon is about 400. It's close to the Earth, and it's smaller than the Earth, but it's exactly the right size to just block out the sun, just block out the disk of the sun. It's like I always think if you bring your thumb up, you can probably block out something in the distance. Even though your thumb is a lot smaller than the thing in the distance, you're able to block it out. So the moon exactly blocks out the disk of the sun. So it's not a planet, but we have seen planets going across the sun. We've seen transits of Venus and transits of Mercury going across the sun. Transits of Venus don't happen very often, but Venus the size is such that we can. Interesting, because planets going across a star is the way in which we find out about other planets in other solar systems. So it's called exoplanets. There's a huge amount of research and work going on looking at the transit of planets across stars. The light changes a little bit, only by a small amount, but you're able to determine the orbits of other planets around other stars.
Thank you. And then, can the coronal projections be predicted?
The coronal projections? Not quite sure.
Yes. Yeah, the coronal projection be predicted.
I'm not quite sure what's meant by the coronal projection.
We'll maybe see if someone can elaborate on that question.
Can you just explain a little bit what you mean by do they mean the eclipses or?
We'll see if they come back to us on that one with a
Okay, thank you. Sorry, I don't quite understand what the question is.
And will solar flares and other solar activities occur in black holes and other singularities?
Oh, people love black holes, don't they? Now, it's a bit sad, really. Well, it may not be sad, it might not be sad. But if our sun were 10 times more massive, what would happen in the end of its lifetime would be that it would end up as a supernova, which is one of the huge explosions in the sky, and then its core would end up as a black hole. But it's not quite massive enough to do that. Now, the question was, can solar flares be seen on black holes? Is that the question? Yeah. Okay. Well, not really, because everything is sucked into a black hole. You can see X-ray emission coming from a black hole as stars are screaming as they pulled into the black hole. Then they kind of scream out in X-ray emission, and we can see material being pulled into the black hole. But we can see solar flares on other stars. So there are other stars which are called very active stars, and they produce solar flares and X-ray emissions. Even that some of them are very much bigger than the sorts of solar flares we've seen on the sun. These are stellar flares. So some of them are huge, supermassive flares on other stars.
Thank you, Helen. And then we've got, what are the different kinds of eclipses?
Okay, well, there's solar eclipse and there's a lunar eclipse as well. So a lunar eclipse would happen when the Earth goes between the sun and the moon, and it's called, sometimes it gets a sort of reddy color. The moon goes dark, but it turns into a sort of red moon, and that's because it's like the light from the sun's coming around like a little bit like happens at sunrise or sunset through an angle in the Earth's atmosphere and causes the moon to be red. Now you can see the moon for a lunar eclipse. You can see it in many places all over the Earth, many places. Whereas for a solar eclipse, the path is very narrow for the solar eclipse. So it's a little bit different, but they're very different phenomena.
Great, thank you, Helen. That's been really, really interesting. That's some great questions there. So thank you, and some brilliant answers. Thank you. But I'm afraid that's all we've got time for now. So thank you so much for joining us. It's been lovely to have you here with us today. And thank you.
Lovely. Okay, thank you very much. It's been lovely to share my passion for the sun.